In this example, we'll be creating a function to model the decay of a radioactive material. So the function we're going to create is going to tell us how much material we have left at time t if we're given the amount we have initially, that n0 or n0, and the decay rate of that material, which will be lambda, and then how much time has passed t. So first, we're going to create the function that will model this in general for any material that exhibits this sort of decay rate. Then once we have our model created or our function created to calculate that, we're going to apply it to a specific incidence where we have a sample, a 7 picogram sample of polonium-210 that has a specified decay rate, and we're going to see how does the amount of the substance vary over time, and we're going to make a plot using the function that we just created. So first thing, I'm going to take this equation and create the general function that we'll use for the second part as a function in MATLAB as its own M file. Then I'm going to create a second M file that is going to be what I'll call the driver that's going to call the function we made and apply it to this specific sample. I'm going to be doing this as a live example, so I have not already solved this, so you'll be going with me on the journey of creating the function and testing it out and making sure that everything works. So you'll be able to see my process as I go about solving it. So like I said, the first thing is we want to create a function for finding the amount of material that's left over some time span. So I'm going to have a function, and my output I'll just call n. That way it matches what was written on the slide. It doesn't have to though. And I am going to call it, just to be consistent with the rest of these files, CMPSC 200 L02 decay. Notice I actually already did save this file, so it has to have the same name. So it's going to have inputs of, I'll do t, which will be able to be a vector of values because I want to be able to calculate this for multiple times, because the eventual goal is to use this to plot how much of the substance there is over time. So t, I want to allow it to be a vector. N0, I will call it. That's the amount of the substance that we start with. And also that lambda. I can't use Greek symbols within this, so I will call it big L for lambda in my function. And I'll build this, I'll put a return there at the end. And I'll save it. So far it's giving me little underlines here because I'm not actually using the inputs yet, and another underline here because I haven't defined big N in my function. I just have kind of the skeleton built for it. And do notice, again, the name of the function, I call it CMPSC 200 L02 decay, matches the file name. And I'm in the same folder where this file exists. So there's the file we're working on, and that's our current directory. Otherwise, we could use this change. We want to make sure everything's in the same folder so that we'll be able to use this in the second step where we're going to call the function. All right, so actually defining this function is pretty straightforward. We already have the equation that's given to us. So the amount of the substance n was calculated as n0 times e, which I'm using that exponential of negative lambda times time. And it's actually that straightforward. Just to remember, if we look in the help for exp, so that's just the exponential function. So if we want to do like exp of 1, that's e to the first power, which 2.71828, etc. It's only giving us a couple of digits here. But I'm going to use that exp function. We do want to keep in mind here, I'll put some notes in my comments. T is a vector, or should be able to be a vector, whereas N0 and L are scalar. Right, so let's see how this works. Save some space here, and I will suppress this output. And I just want to test my function for some values, make sure it runs at least. So in the command window, just for the moment, I'm going to call it for t from 0 to 10, just so I can get some values out here. N0, I'll just say I start with 100 of the material, and then my lambda here, my decay rate, I'll just, again, kind of choose something, 0.2. So these are just arbitrary numbers just to see does it even run, and does it deliver what we expect. Okay, so it gave us this output. I guess I'll save that as n. I'll call it little n for now. And it gave us 11 values, and our t also has 11 values because it's 0 to 10. So let me just put a t in for here while we're testing it. All right, so we get a value of the material that's remaining for each of these times. Here I just chose 0 to 10 seconds. So this is the amount of material at 0 seconds. Well, it should be 100 because that's our initial amount of material. And then we have at 1 second, 2 seconds, 3 seconds, all the way up to how much we have left at 10 seconds. All right, so building the function actually really quick in this one. But what we want to note is I made the function take 3 inputs. The order I put them in, again, didn't really matter. I put t first. I chose to do that kind of out of habit because t is going to be a vector, and if we were to use this in another subsequent function like an fmin search or an f0, I just like having the vector quantity first. But if you put this in a different order, that's perfectly fine. So t, the time input, which can be a vector of time, and n naught or n0 here I'm calling it, the initial amount of material, and L, the decay rate. Now here, t is a vector quantity, but notice I don't have to actually use in this one any dot multiplication because in the exponential, I have a scalar times a vector t. So whether I put one or not, in this case will work okay. So I'll just show that I can put one there. It won't make a difference here because it's a scalar times a vector. exp already can handle scalar, vector, or matrix quantities. So having a vector in its argument is going to be fine. n0 is also a scalar. This is going to be a vector. I'm having a scalar times a vector, so again, just a regular multiply or asterisk is fine there. But if I did put a dot there, it's going to behave exactly the same. As we see, exactly the same results there. So this is a case where with the dot or without the dot will be the same, but always be aware, do you need a dot multiply, dot divide, or dot exponent when you are dealing with vectors? And other things to note on this function is that, well, I have some blank space up here. I could put in some initial comments, but the first thing that is not a comment or white space is the word function. So then MATLAB knows that this is a function with the name comsci200 L02 decay. And it takes these 3 functions, these 3 arguments. With the function working, now we can apply it to our specific problem. So I am going to just make sure this is saved, and I'm going to go to what I'm calling a driver file. So this is the script I'm going to write that is going to use the function I just wrote to solve this specific problem. Remember, the function I wrote, this is general. This will work for any substance that experiences this exponential decay, and I can customize what the initial amount is and what that substance's decay rate is. Now I go for the specific. So in the script, I will go with a clear, a CLC, and a close all to make sure I am always starting from scratch. So when I run that, look, the workspace is gone, the command window is clear, so I have a nice clean starting place. Now, in this particular case, I was told that we want to model this polonium 210. So we're going to have, in this specific example, an initial amount of the substance I will call N0, and we're told it's 7 picograms. So 7 times 10 to the negative 12th, and I want to make sure initial amount of polonium 210, and this is in grams. So I'm using base units here. And I want to put that comment there to remember, well, what it's representing and the units it's in, because these are engineering problems, so probably we're going to have units. Now here it was only 1 line of code, but I guess I really should put what does it do to calculate amount of substance at time t. It's only 1 line, so it's very simple. We're going to get certainly more complicated functions, but commenting is really important so that, well, we as the author know what our code does, or remember if we come back the next day or week or year, and someone else using our code knows what we were doing. All right, so back to the driver file for this specific case. So the initial amount of the polonium in grams. I am calling it N0 here. We'll see it actually doesn't matter what I call it as long as I'm consistent within the script. So I'll show that in a little bit. The same thing with L. This is going to be our decay rate. And for this substance it is going to be 0.005. And this will be in inverse days. So decay rate in 1 over days. And I'm going to have to see how much of the substance is left over time. So I'm going to make a time vector. Now I'm going to do this as a linspace because I don't really care about the spacing between them. I just want to make sure there's enough days or enough density in my vector that I get a good picture. So I want to start at 0 days with the initial amount. And this is a case where I don't know how long it's going to take up front. I mean, I could do the math and I could see how long it takes to really get really close to 0. So for right now, I'm just going to do it out to, I don't know, let's say 500 days. And I'm going to use 1,000 values of t. So this will be time. Oh, and notice here, the t automatically is, well, not automatically, but I have to specify this will be in days because of the decay rate is given in 1 over days, then t in base units is going to be days, so that the exponential will be in 1 over days times days will just be unitless quantity. Right, so if I had a different substance that maybe decays much faster, this L could be in minutes or seconds or milliseconds even. My T, I would want, again, in base units to match that decay rate. Okay, so I've specified my specific parameters for the polonium-210. So let's see how much we have over time. So I'm going to say that my n equals, and this is where I can use the function I've already made. And actually, just for simplicity, I'll copy this so I don't make any mistakes. So I am calling it with, I'm calling the function I wrote in the other file with this specific time, right now 0 to 500 days, this initial amount, 7 picograms, or 7 times 10 to the negative 12 grams, and this decay rate, 0.005, 1 over days. So I have to call the function still so that I can make the n for my specific case here. So let me run this. Right, make sure everything is working the way we expect. All right, so n has 1,000 values because we have 1,000 values of time. So that's good to see. And I did not suppress the output, so it prints it to the command window, but I don't really need to see it because I'm going to graph it in a minute. So I'll rerun this and see our workspace has our values. So I think I put a large upper limit of 500 days that it's probably more than I really need, but we can check what the plot looks like and then come back and make that upper limit lower if all the interesting parts of the graph are already done by the time we have reached 500 days. So I want to plot now my results. I want my t to be my independent variable. N that I just calculated is my dependent variable. And I will plot this, well, I'll just use the defaults for now just to see what it looks like before I spend time making it fancier. So actually here, 500 days, I guess wasn't enough because eventually all of the polonium is going to decay. And we see that even after the 500 days, we're still not all the way down near 0. So the 500, again, that was just my initial guess. I'm going to increase it just so I can see it get towards 0. So it's okay to redo this once we see the graphics. All right, now we see that it did by about, I don't know, 1,500 days, maybe a little bit before that. It is very, very close to 0 and only getting closer. So now I would say, let's tighten this up to about, well, I'll see what 1,500 looks like. So this might take a couple of times of rerunning it to get the picture to really look like something that that's going to be meaningful to us. I'll tighten up just a little bit more, let's say 1,250 days. All right, that looks pretty good for our use here. We see that initially we have the 7 picograms, and then it is decaying. It's decaying over time, and it starts to get really close to 0 as we are going forward in time. And I'm going out to 1,250 days. We have a little bit of extra white space here, but we'll take care of that in a minute. All right, so first thing is I'm going to make this a black line instead of the default blue. I think that looks a little bit better, and the contrast is better when we use a black line. All right, now I'm going to finish up my plot with all of the things I want. I like always showing the grid when I make a plot. I think it's a little bit easier to see where the crossovers are on different pieces of it. And now I want my labels. So my X label in this case is going to be my time. So that's time, and I want the units. In this case, it's days. And I like making a larger font size to make it more readable. So I'm specifying a font size of 14 for this. If I don't specify a font size, let's just compare it quickly. I don't love the default sizing for the labels or for the tick marks or the tick labels either. I think they're a little bit small when you paste them into another document. They might be fine to look at in the figure, but they're a little small for other uses. So I think 14 at least, it looks a little bit better when you then paste it into a document. So I will specify that. So that is my X value. And my Y label, this is my amount of polonium-210, and this is right now in grams. And I'll also use a font size of 14 for this. All right, so the amount of polonium-210 in grams over time is specified in days. And I can also make those tick marks bigger by using the set GCA and then specify the font size of 14 here. All right, so notice it made those tick labels larger, which again, it's going to be easier to see if I use this in a document later. So this is not bad here. It shows the general trend, this exponential decay of my polonium-210 over time. So by the time we get to about 1500 days, pretty much all of it has decayed from its original 7 picograms. Now I want to change this up a little bit just to show some differences now that it's working. So like I said, I am out of convenience calling, for example, this N0, and that does match how I named it in my function. But it doesn't have to. I'm going to call this something completely different. Let me call this Q, and then I have to change it here as well. Now it doesn't, the function doesn't care about what I call it in this file. Here I'm calling it Q, and I'm going to pass it, we call it, into the function, that value of Q. But once it gets into here, it knows it as whatever this value is when we call the function knows it as N0. So in each file, the variable name has to be consistent, but between files, it does not. But it is always true that the second value I pass in is going to be N0, which represents in my function the initial amount of my substance. So if I run this, it runs exactly the same, as long as I call it Q in both places. So we don't have to be too concerned about naming it exactly the same. It might be convenient so that we know between files that it's exactly the same variable or what that variable represents, but it doesn't have to be. And let me increase this a little bit more. I think it's dense enough, but I would recommend not using the default 100 for linspace. I think it easily will make it a little bit too choppy. So I like to use probably at least 1,000 data points, unless there's a good reason to use fewer than that. I think 1,000's going to be good. So you see it's nice and smooth. I up to here to 10,000 and it still runs fine. All right, last piece here, because everything is really small, I have here the polonium in grams, and we see that up here I have 10 to the negative 12. That's fine, but maybe I want this in just a different unit than grams. So let me instead plot this in picograms. So I'm going to take the amount of my substance and I'll multiply it by 1 times 10 to the 12. But then down here, I have to change the unit I'm working in. Right, so really nothing has effectively changed. It's just the plot looks, the y-axis is just scaled differently, but it's telling the same story. So again, in the plot, my N is being calculated in grams. So I will specify that here. Amount of substance in grams. But so I'm not changing n, I'm just changing how I plot it. I'm multiplying every value in n by 1 times 10 to the 12, so I'm going to go from representing it in grams to representing it in picograms. And that's why then here in the y label, I also changed that. So now in the plot, I'm starting at 7 picograms and going down towards 0 picograms. Oh, the other thing I wanted to clean up here is I'll put an axis tight on so that I eliminate some of that white space. Now it goes out only to the 1250, since that's the amount of time, the maximum amount of time in days that we were simulating. So it's a little bit tighter, it gives me just a little bit more detail as I go through. So the tight axis here, I'm starting at exactly 7, and I'm ending at 1250 days. So this has completed what we were asked to find. We first started by making that general function that I made take 3 inputs or arguments: the time, the initial amount of the substance, and my decay rate. So it's a very general function that's good for any exponential decay type of function if it's radioactive decay. I could also use this if it was exponential growth, like a bacteria colony or something like that, if I put in a negative decay rate instead of a positive decay rate. But this is just the general equation then that I've created, or function that I've created. Then what I do is I made a script file. Notice this one's a script. I am clearing on the script. I am not clearing on the function. In the script file, I'm going to define the specific parameters I want to use for the problem I'm trying to solve. I then use the function that I've already made in the other M file, and then I'm plotting my results. And also notice that both of these files are in the same folder. So that way, when I use the driver, it knows this file that I'm talking about, or this function that I'm talking about. If they're in different files, then that's not going to work. If they're in different folders, it's not going to know what CompSci 200 L02 decay is. So that's the complete function and the plotted results in the end.